Welcome to Multiple Choice Question 6 of the 2008 Mathematical Methods Exam 2. In this video, we will be looking at the solution for this question. A reminder that this video is in no way endorsed by VCAA. And now, before we move on, I just want to point out that the use of a CAS calculator may assist in answering this question. So for question 6, we have the simultaneous linear equations given below, where A is a real constant within those set of equations, have infinitely many solutions when A is one of the following. So there's a couple of ways of approaching a question like this, and the first method that I'll show you is actually by considering the gradient and the y-intercept. So to have infinitely many solutions, we actually want the same equation for both of them, so that they represent the same straight line on a Cartesian plane. So for infinitely many solutions, we want the same gradient and the same y-intercept. So if we consider our first equation, ax plus 3y equals 0, we can rearrange that for y equals so that it's in gradient intercept form. So we could start off by going 3y is going to equal negative ax, and that's when we subtract ax from both sides. So that means that y is simply equal to negative a divided by 3 times x, and then technically there's a plus 0 there. And I've just put that there so we can identify what the y-intercept would be. For the second equation, which is 2x plus a plus 1y equals 0, we can start by subtracting the 2x. So we get a plus 1y equals negative 2x. So therefore, y is going to equal, and we're going to divide by a plus 1. So we're going to get negative 2 over a plus 1 times x. And then again, technically there's a plus 0 there, which represents the y-intercept of that line. So looking at the y-intercepts, which is the plus 0 at the end of both equations, we can already see that both equations have the same y-intercept. So all we need to do for this question is force these two equations to have the same gradient. So if we want them to have the same gradient, that means we want negative a divided by 3 to be equal to the gradient of the second line, which is the coefficient of x, which is negative 2 over a plus 1. We now want to solve that equation on a CAS calculator. So going into the main menu, we want to type in that equation. So we first of all need to bring up a fraction, so we can put in negative variable a, and that's divided by 3, is equal to the fraction. And then we had negative 2 divided by, and then it was variable a plus 1. And we want to solve this for a. So we go interactive equation inequality, solve for the variable, and we replace that with a and hit OK. So from the calculator, we found that the two values of a that would give the same gradient would be a equals negative 3 and a equals positive 2. So looking through the options, the same way of storing that information is to say that a is an element of the set of negative 3 and 2, which makes b the correct answer for this question. So from the examiner's report, we can see that this question challenged a lot of students, with only 45% of students getting the correct answer for this particular question in the exam. I'd now like to show you a second method that you can use to do this same problem, and that's going to involve matrices and a thing called the determinant, which you may have heard of before. So looking back at the problem, it asks for the values of a where we'll have infinitely many solutions for that system of simultaneous linear equations that we've already been considering. So this method relies on us converting the system of simultaneous linear equations into a matrix system. So what we're going to do is we're going to set up a square matrix that's going to multiply x and y, and then that's going to be equal to another matrix. So to do this, we're going to look at the coefficients of x, which are a in the first one and 2 in the second equation. And we're going to put that a and that 2 here, because we know that's the position in a matrix that would multiply x. And then we're going to consider the coefficients of y, which is 3 in the first and a plus 1 in the second, and we're going to put those in this position here. So we're going to have a 3 in the top right, we're going to have a plus 1 in the bottom right, and again we put them there because they are the positions that would multiply y in that matrix. And then what it equals, so for the top one it's 0 and for the bottom one it's 0, we're going to put in that matrix on the other side of the equal sign. So now to have infinitely many solutions in terms of matrices, what we require is for the determinant to be equal to 0. So that would give us infinitely many solutions, or it's possible that it could give us no solutions, and then that would depend on the y-intercept. So just to recap the determinant, if you're not really familiar with it, if we consider a matrix A, which is a square matrix with the elements A, B, C, and D inside that matrix, then the determinant, which I'm going to represent as det of A, is going to equal A times D minus B times C. So now if we apply that rule, we're going to have AD minus BC. So A times D in this case is actually going to be A, and then that's going to multiply by the D value, which is A plus 1. And then we subtract away from that the B times C value, where in this case B is 3 and C is 2. And we're going to let that equal 0, because that will give us infinitely many solutions, or again, possibly no solutions. But the way that this is set up, it actually leads us to the infinitely many solutions, because we've already seen, thinking back a few moments ago, that the y-intercepts were the same for this line. So now we have an equation that needs to be solved. I'm going to flick back over to the calculator to see how the calculator could be used to approach this question using the determinant approach as well. So for this second method, on the calculator, we want to type in that square matrix. So I'm going to go to Math 2, where I can find this button to put a square matrix in. And we're going to put in the first position A, and then we had 3, and then in the bottom left it was 2, and then the bottom right had A plus 1. And on the calculator, we can highlight that and go interactive, and then it's matrix calculation det, and that is an expression for the determinant of that matrix. And we're going to drag that down and let it equal 0, and we want to solve that equation for A. So we go interactive, equation inequality, solve for the variable, and we need to replace that with A, and hitting OK gives the same A values as we previously found. So once again, the calculator gave us that the values of A that come out of that equation would be A equals -3 and A equals 2. So that does show that B is the correct answer for this question. And I do want to just stress that if the y-intercepts hadn't conveniently been both 0, you'd need to test when A goes into those sorts of equations. So in different questions to this, you'd have to test whether those A values give no solutions or infinitely many solutions. In this case, both values give infinitely many solutions. So the final thing that I'll show on this video is that if we use those A values, we do get infinitely many solutions, and I can show that by graphing them and showing that they are in fact the same line. So if I start with variable AX, and then it was plus 3y equals 0, and then we do math 3 given that A equals -3 to start with, that's the first equation we'd get. And then if I just drag that down actually and modify it slightly to give the second equation, which was 2x, and then the thing that multiplied y was variable A plus 1. And then if that equals -3, that's the equation. And dragging those two down, you can see that they sit perfectly on top of each other. And if I did the same thing for when A equals 2, so if I just drag this down and do A equals 2, and then same thing with the second equation, drag it down and change A to be equal to 2. We get two more equations, and dragging those down, you can see that both of those equations are exactly the same line as well. So that goes to show that we have in fact found values of A that give infinitely many solutions.